Hello again, everyone. Here is another non-linear ordinary differential equation in equation 1 on the slide. We can simplify this ODE, which currently looks very complex. So what we do is we use the substitution um, P equals dy by dx. So I'll just write that down for you. We To solve equation 1, we use the substitution right, P equals dy by dx, and then differentiating both sides of this expression, we get d squared y by dx squared, and that's equal to dp by dx. So now we substitute p equals dy by dx into the left-hand side of equation 1, and we substitute dp by dx in for d squared y by dx squared on the right-hand side of equation 1. So we get 1 plus p squared, and that all of that on the left-hand side is cubed, and that is equal to dp by dx on the right hand side, and that's dp by dx all squared on the right hand side. So we'll call that equation 2. Now, to get equation 2 into any kind of a form that can be solved, we need to get rid of the squared term on the right hand side, because we don't want dp by dx all squared. What we want is just dp by dx on its own. So square rooting both sides of equation 3, we get dp by dx equal to 1 plus p squared, and then put brackets around that, all to the power 3 over 2. So that is equation 4. This means that we've got it in a form that can be easily separated out. So if we separate out the terms, we've got dp divided by, and then in brackets, 1 plus p squared, all to the power 3 over 2, and that's equal to the integral of dx. Now, we've got it in a more simplified form that when we make the next substitution will be easier to integrate. So we substitute, let me write that down for you. To solve, we substitute p equals the hyperbolic sine of v, and this means that dp is equal to the hyperbolic cosine of v dv. Right, I shall refer to the hyperbolic sine as shine and the hyperbolic cosine as cos or cosine. So the hyperbolic sine is shine and the hyperbolic cosine is cos or cosine. Now, if we substitute p equals shine of v into the left-hand side of this equation, and dp, if we substitute into dp cos v dv up here, we get cos v dv divided by, let me get that line a little more straight. Right, there we are. So we've got in the denominator 1 plus sine squared v, close bracket, to the power 3 over 2. And in fact, let's just make that look a little less cluttered. Right, put the dv there, and that's equal to the integral of dx. Right, so how does this help us? Well, the reason why I've chosen the hyperbolic sine or sine of v as a substitution for p is because you may recognise that 1 plus sine squared v is actually equal to cos squared v. So let's go on to the next slide and have a look at that. So we know that, I should really put we know that cos squared v is equal to 1 plus sine squared v. So if I just go back to the previous equations, I should have labelled them. So let's label that one as 5 and the last one as 6. Let me just write that a little more neatly. There we are. Not easy writing on these pads. So equation 6 becomes the integral of cos v, and we've got a dv there as well, divided by cos squared v, and all of that is to the power 3 over 2, and that's equal to the integral of dx. Now, the left-hand side can be simplified really easily because the denominator is simplified simply by way of multiplying these indices together. So 2 times 3 over 2 just leaves you with 3, or a cubed term. So this can be rewritten as cos v, and we'll put the dv term there, all divided by cos cubed v there, and all of that is equal to dx. So we can simplify the left-hand side of this last equation even more. Let me just put some more equation labels in. So we'll call that equation 7, and the last equation we've written down we'll call equation 8. So equation 8 therefore becomes, so we'll say simplifies to the integral of 1 over, get that a nice straight line, 1 over cos squared v, and then the dv there on the top, and that's equal to dx. Now we can simplify this left-hand side a bit more. This becomes the integral of sec squared v dv, and that's equal to the integral of dx. I haven't integrated the right-hand side yet because I wanted to do all of the integrals at once. So the integral of the left-hand side of equation 10, so the integral of sec squared v dv is quite simply the hyperbolic tangent tan of v, and that's equal to x plus k. Whenever you integrate, you get a constant. But if you do this question yourself in your own free time, you can follow through with the constant being a positive one. So you can keep this right-hand side as x plus k and go right through to the end, and the final solution should have x plus k in it. But for convenience, partly because it makes the solution look a little nicer and tidier in light of what you will recognise it being by putting a minus constant in. I'm going to put a minus constant value there. So we could have had plus k, but I'm choosing it for convenience to minus c1 because it just makes the algebra a lot tidier in the final solution at the end. So we've got that, but we need to recognise that since P equals shine V, then V is obviously the arc shine, if you like, written in this form of P. So V equals arc shine of P. You can actually write it as, well, you can actually write it like that, okay? So V equals arc shine of P. But we know that P is equal to dy by dx. So we've got V equals arc shine of dy by dx, right? Now let's put some equation labels in. So this is equation 11, and we'll call this equation 12. So equation 11 can now be written as, well, we've got a hyperbolic tangent term, haven't we? Let me just go back to that. So we substitute in arc shine dy by dx for v. So we get tan arc shine dy by dx is equal to x minus c1, right? And again, you could write this part as shine to the minus 1. So another way, again, to write it out properly, the alternative way of putting this down is to write fan of shine, inverse shine, really, of dy by dx equals x minus c1. What I've written in red is perhaps the more modern way of writing it. It's the, I don't know if it's that much quicker or whether there's any more brevity in writing down what I've written down in red. Either is good enough, but the second, written in red, is the more modern and conventional way of writing it. But it doesn't really matter. So anyway, what we have to do now is get this dy by dx on its own. So first of all, we'll just label this equation. So let's get the black ink again. So we'll call that, what is it? Equation 13. So 13. I suppose you could say this red version here is also equation 13. It's identical to the one in black. But anyway, to simplify equation 13, we just take the inverse fan, or the inverse hyperbolic tangent of both sides, right? So what we are left with on the left-hand side is just arc shine of dy by dx, and that is equal to, well, we're taking the inverse fan, or the inverse of the hyperbolic tangent of both sides. So what we've got here is fan, the inverse hyperbolic tangent of x minus c1. And to be consistent, I think probably it's better if I just write the inverse shine function like that, so that it's consistent with what we now have on the right hand side. So in the end, we have used the red version here to get to this version. So we'll call that equation 14. We're still not finished because we have to get dy by dx on its own. So what we do is, to get the left-hand side in terms of just dy by dx on its own, solely in those terms, then we take the hyperbolic shine of both sides. So we're left with dy by dx, and that's equal to the shine of, in brackets, than the, well, I'm getting a bit of a mouthful here, aren't I? Shine of the inverse hyperbolic tangent of x minus c1, close bracket again, and we'll call that 15. So I hope that's reasonably clear. So now, what we need to do is separate out this equation and put it into integral form. So that's quite easy because if we go to the next slide, then what we get is, how shall I put this? Rewriting equation 15 in integral form, we get, I have to look at it, so we get the integral of dy on the left hand side, and that's equal to the integral of shine of the inverse hyperbolic tangent of x minus t1 dx. So we've separated basically the variables out to get this, and we'll call this equation 16. So see if we can squeeze an equation 16 on there. Doesn't look very legible, does it? So let's just employ the use of an eraser. So we've got a dx there, and what did I say this was? An equation 16. So yeah, so we've gone from there by multiplying both sides by dx and bringing in the integral signs, we get equation 16 in this form. Right, but how do we solve the integral on the right hand side? The left hand side is very easy. The integral of dy is just y. But how do we work out the integral of what's on the right hand side? Well, first of all, I'm just going to use tables for what I'm about to do next, and that is the shine of the inverse tangent function of a function u, for example, is equal to u over, make this into meter, u over the square root of, I'm not writing very legibly, am I? Let's try and get that a bit neater. U divided by the square root of 1 minus u squared, right? So that's what that's equal to. This means that if we go on to the next slide, we've got shine of the inverse hyperbolic tangent of x minus c is equal to x minus c all divided by the square root of 1 minus x minus c all squared. Right? So that's what we've got there. Now let's just check what we've got. So we've got equation 16, and we know that everything on the right hand side under the integral sign is equal to this. So without integrating the function, this is what this function on the left hand side here is equal to, underlined in green. So let's just go back to black ink. So what we've got is, I won't do the integral on the left hand side yet. I'll leave that as dy. So that's equal to, or more specifically, the integral of dy is equal to the integral of x minus c1 all divided by the square root of 1 minus x minus c1. There we are. And then the dx term as well. By the way, what I should have written on there, if that's C1, that's C1, and that's C1. But anyway, it doesn't really matter. Just being a bit pernickety. So, but we've run into a bit of another problem, because how do we do this integral on the right-hand side here? I think that will be equation 17. So that's equation 17. How do we solve equation 17? Well, we use another substitution. Substitution. Put, I'm going to call it Q, equal to 1 minus what do we have? 1 minus x minus c1 squared. So I'm just putting q equal to the bit inside the square root sign. And that happens to be q equals 1 minus x minus c1 squared. Now, to differentiate that, we get dq equals, well, the 1 disappears. We've got a minus sign there. And differentiating this is just like differentiating u squared. You get to u, except the u is x minus c1. And then when you differentiate the u itself, well, the u is x minus c1. So you just simply multiply by the derivative of everything inside those brackets, and that is 1. And then you've got a dx there. But we don't need to put that term 1 in there. We can just write down straight away dx. So we've got dq equals minus 2 times, in brackets, x minus c1 dx. And this means dx equals dq, in fact it's minus dq, all divided by 2x minus c1. There we are. Does that look legible? I think that will be hopefully okay. So, equation, let me just go back. Equation 17 can now be, be rewritten as, let me go into the next page. So we've got the integral of dy is equal to the integral of, well, we've got an x minus c1 on top, but in the denominator, so the lower part of the fraction, we've got the square root of q. And then we've got dx here, but the dx is equal to minus dq over 2 times x minus c1 here. So if we just erase that dx term, then we've got we've got a minus sign here, haven't we? So we've got dq all divided by 2x minus c1, right? dq over 2 times x minus c1, close bracket, and then we've got that minus sign which I've already put in, and straight away you should be able to see that the x minus c1s cancel, and we're left with the integral of dy is equal to minus the integral, in fact it's minus a half of the integral of, how shall I write this? Well, I've got a square root on the bottom, but if we bring it, if we can also rewrite what we've got on the right hand side as dq over q to the half, right? So everything there where we've cancelled out the x minus c1 reduces to this equation here, and we'll give that an A. So that was 17. We could call this 18, just 19, 20. So we'll call this equation 21. So we've got to equation 21, and hopefully you will recognise this is quite elementary to integrate and to solve. So integrating, we have, in actual fact, there was something I forgot to do, and I was getting a bit muddled there, so many apologies. But this equation 21, first of all, before we integrate, can be written as dy equals minus a half of the integral q to the minus a half dq. That's the mistake I was making before. I was forgetting to put the equation into that form. So now we've got equation 22. Right. So we're on track again. So you should recognise, as I said before, even with the previous one, that's quite elementary to integrate and solve. So we can go ahead and do that. So the left-hand side integrates to give y, and then we're left with minus a half. Well, what's the integral of q to the minus a half? Well, that's just q to the half divided by a half. And then you add a constant on, and this time we'll leave it as constant 2, right? We're leaving it as plus c2, not minus c2, but plus c2. It's a little bit of tweaking I'm using that will become evident. Now, this can be simplified to give y equals, well, we've got basically a half divided by a half, which is 1. Another way of rewriting this, which I'll call equation 23. Another way of simplifying this is first, if you divide the q to the half by a half, you get 2q to the half. And we've already got that minus a half there, plus c2. And of course the 2's just cancel. So what I'm going to do is just, instead of doing all the working for that one, which I've done anyway, but now erased, we get minus q to the half plus c2. Now, but we know that q equals 1 minus x minus c1 all squared, don't we? So, equation, I didn't label it, did I? So we call that equation 24. So equation 24 becomes, and I have to look at it, y equals minus q, it's minus, y equals minus q, but q is 1 minus, in brackets, x minus c1 all squared. Am I doing it right? Yeah? So going back to that, yes, yeah, and we have a plus c2. Right, now we can simplify this a bit more. And the reason why we're going to simplify it is because it becomes a particular equation that you should be quite, with which you should be quite familiar in effect. So, simplifying further, well, what we want to do is bring the C2 over to the left-hand side. So we get y minus C2, and that's equal to minus, in brackets, 1 minus x minus c1 squared. And is that raised to the power or anything? Let me have a look. I don't think it is. So, it's actually, I think I have been making a mistake, haven't I? So if we just go back, yeah, so it's q to the half. So that should be to the half. And that should be to the half. Just a little slip, a little error that I made, but it doesn't alter anything because it's what we've done up to now is now correct. So we've got y minus c2 equals minus 1 minus x minus c1 squared, all to the power of half. Now, if you square both sides of, and we will call it, what equation should we call it? 24, 25, and 26. So if we square both sides of equation 26, we get y minus c2 all squared, and that's equal to 1 minus x minus c1 squared. If you square this, all of this bracket to the power of half, that a half term just disappears because you squared both sides of equation 26. So, therefore, we have, well, we can simplify equation 27 a little more. And so we get y minus c2 all squared, y minus c2 all squared, plus x minus c1 all squared equals 1. And you could rewrite that as x minus c1 all squared plus y minus c2 all squared equals 1. So we can see here we can see that this is a circle with center C1, C2, that's meant to be a little comma there, C1, C2, and radius can't spell radius, can I? Let's just oops, and radius r equals 1. Right, okay, and that is basically that. So just to recap, we've gone from this equation, equation 1, which looks extremely complicated and in fact almost insoluble at first glance. We've gone from that to the equation of a circle in equation 28. So we've got equation 28. Oops, I've written it in red. Never mind. So that's values and judges actually. So we can highlight that more clearly. The equation of a circle. Well, I hope you've enjoyed that, and that you will come back and watch more of my videos. So I'll say goodbye for now and see you soon.